All right, so the span of the row. So basically, if you think of the row space as the same idea as a column space, just with respect to the rows as opposed to the columns, it's probably a good way to get started on it. And in fact, it kind of starts to get us along the lines of thinking under what circumstances is it okay to represent a vector as a column, and in what cases it's okay to represent it as a row. So it's kind of leading us down that road. Right, so the span, which is a vector space under standard matrix addition and scalar multiplication, is referred to as a row space. Right, so we'll kind of tackle that in a minute. And then the column space we already know about, or the span of the columns. Definition of row equivalence, I think that's probably something that I could take for granted. I threw in a few examples just in case. But if you have your matrix A performing some elementary row operations, we get B1, 2, and 3, but they're all row equivalent to A, right? Which means that they're all made up of the same vectors, row vectors, just either juxtaposed or involving scalars or something like that. But it all has the same framework. Right, this one is just switcherooski on this one. This one has a scalar multiple, and this one is a row addition. All right, so what it would mean is that there would be one pivot, because, oh, actually, no.
Each one would have the same pivot.
Each one would have the same, yeah, that's what I was trying to get. Correct. Okay, so A and B are two m by n row equivalent matrices, and the row spaces of A and B are equal. Right, so you're talking about using reduced row echelon techniques on any one of these matrices. The result is going to be the same throughout, right? Making them row equivalent. All right. Now to find the bases, transform into reduced row echelon form. Non-zero rows of the matrix in reduced row echelon form give the bases of a row space of A, which I think hopefully would kind of feel like at least would be a true statement. The second one is something we've been working with all semester, so I don't think there's anything new there. To find the basis of a column space, to find the basis of the vector space, which we, right, and that's justified by this bad boy here, because the dimension. Well, I think it was getting late last night, so hopefully I put it in here somewhere. But the idea is that the row rank and the column rank should end up being the same, and therefore give us the rank of the matrix. All right. So, well, anyway, the dimension of the row space of A is called the row rank of A. So again, this is the row space, not the null space, right? Because we talked about column space and null space, and it's very easy, or at least when I was a student anyway, it's very easy to kind of juxtapose null and row in your mind, so just be careful about that. Dimension of the row space, so reduced row echelon form, anything that doesn't contain zeros in it is going to be a basis of the row space. All right. Once you've established that, you now have the rank, the row rank. You would also then have the column rank based on the normal techniques that we would use. All right. The row rank and column rank are equal. Since the row rank and column rank are equal, we refer to the rank, just a single rank of A. We don't say row rank or column rank. What we do is we use whatever is more convenient to determine what the rank should be. All right, so if you have something that's in echelon form, I guess you can go either way. I'm just trying to think of a situation in which it's more convenient to go one way as opposed to the other. With calculators, it's like, who cares? You just ref it, and you're like, well, the pivot's good. I got one row of all zeros. Good. So I got it either way. So at a minimum, you can use it to verify. So dimension of the column space we call the rank of the matrix, all right? And the dimension of the null space, so back to the null space, is the nullity of the matrix, right? And those two things should add up to equal n. Right? And we talked about this in the last example. So we had the dimension of the column space and we had the dimension of the null space, and I could even refer to it. Dimension of the column space, 1, 2, 3, 4. Dimension of the null space, everything else, should add up to equal n being the number of columns within the matrix because it's defined as an m by n matrix. All right, so all we're doing now is slapping a name onto these things. This guy we're calling the rank, and this one we're calling the nullity. And the row space would then be equal to the rank, but that's only in a in an n by n. All right, so bases and rank of the row and column spaces of A, if A is given. All right, so four by five. Yeah, the rank is going to be the dimension of the column space, yeah. All right, so do reduced row echelon on A. Get this jammy. Not that jammy, this one. All right, so a little RRF action. All right, identify the pivot columns. All right, so we're looking at I don't know how I want to write this. Basis column space of A would be C1, C2, C4. Dimensions column space A be equal to 3, and therefore the rank is equal to 3. All right, so the row space, again, is just anything that's not a 0 row. All right, so the basis of the row space of A would be R1, R2, R3. Get rid of that equal sign. I'm trying to be consistent here for a change. R1, R2, R3. So anything that's not entirely composed of zeros. So dimensions of your row space is equal to 3. And so the row rank is also 3. All right, so it's not a proof, it's a justification that we can say that the ranks are equal. So therefore the rank of the matrix is going to be whatever those two ranks are. So figure out one of them and you got them both.
So the row of the rows, the dimension rows in the null space is different.
Dimension of the null space is different, correct? Right, because that's the number of free variables. So the dimension of the null space would be 2. Just making sure I didn't ask that. Actually, it's a good thing to throw in. I'll take that as a typo. Dimensions of null A would be 2. Just to really emphasize the difference. All right, so now the next one is in reduced echelon form, right? I mean, it better be. I mean, it's zeros and ones. I mean, if it's not, then I don't think I understand what reduced echelon. That would lead to a free variable, a single free variable that would correspond to the free variable, one of the free variables in. All right, so again, we're looking for the bases. So the row space, the basis of the column space, the basis of the row space, the rank, and the nullity. Right. So the basis of column space of A would be the first 3 columns, right? So the rank of A would be equal to 3. So we can kind of cut out the fluff. We don't have to state the dimensions. I mean, we didn't have to state it in the previous one either, but just to kind of connect it. All right. The nullity is, again, the dimensions of the null space. So if I know, I mean, I don't think it was needed to be stated that n is equal to 5, you can count 1, 2, 3, 4, 5. But just to kind of really accentuate it, the nullity is everything else. So the nullity is equal to 2. And so I just need the basis of the row space. Which is anything that doesn't contain a row of all zeros, so R1, R2, R3.
Why is the nullity 2 again?
Because the sum of the rank and nullity equals n. N is the number of columns within the. And also, we were talking about the basis of the column space and the basis of the null space. That the basis of the null space is always made up of the free variables. So once we identify the pivots within the column space, we're looking at these making up the basis of the column space. So everything else is going to make up the basis of the null space. I have this habit of writing important result, and it's kind of like when you highlight everything on a piece of paper. It's like you're highlighting nothing. It's a result. It may be important, but it might not be important to you. All right. Yeah, let's just put it this way. At one point, it was really important. And that point was when I didn't know how to use the graphing calculator. Because then things like this became really useful. Like an n by n matrix, A is non-singular, meaning it's invertible. You can find the inverse of it, if and only if the rank of A is equal to n. I was like, wow, that's great. because I can easily, especially if it's written like this, I could easily figure out the rank of the matrix. And once I figure out the rank, I can determine whether I need to even bother finding the inverse. That's awesome. But now I have a calculator. I just type the matrix in, hit inverse, gives me an error. It's not invertible. Then I just got to figure out a way to justify it. I can get stuff right on a test now without even knowing anything. It's great, But no, but really, all kidding aside, the justification is kind of cool because the rank, if the rank is equal to n, you're talking about a pivot being in every column, right? Right, which means that you don't have a row made up entirely of zeros. One of the conditions, or one of the, you start off with a simple example, just a 2 by 2 matrix. If you put a row of all zeros in there, you're getting a determinant equal to 0. If you get a determinant equal to 0, then your determinant shortcut technique for finding the inverse doesn't work because you get an undefined coefficient. Right? So if the determinant's equal to 0, then you're not going to be able to invert your matrix. Right? So all of that is like, it's a logical progression of like, if this is in place and that, and that, and that, then that. But it all comes to this important result, which just boils down to, like, if you know the rank, then you can determine whether it's even worth bothering trying to invert your matrix. All right, but these are like FFOTD, fun facts of the day, because all of this stuff is like, you could figure it out with a calculator or GeoGebra. I'm not saying that there isn't value in it, but it's kind of like finding the standard deviation by hand in the stat class. There's value in knowing how to do it, but there's also value in preserving time in not doing it that way. So that's kind of the moral of the story.